Hi, my name is David Cramer. I'm going to talk to you about our research on multitask combinatorial bandits for budget allocation. We're a team of researchers at Amazon. We have interns Lin, Yang, and Jianing, and we are made up of applied scientists, economists, and a product manager. We're going to talk about demand-side platform. Demand-side platform, like Amazon's DSP, allows advertisers to advertise and get their marketing message across the web. DSP allows access to inventory such as display, video, audio, across inventory that's on multiple websites, apps, and Amazon's own property in this case. When an advertiser uses a DSP, they set up a campaign. A campaign will have a marketing objective, and it will use different tactics, such as different audiences and channels, to reach and achieve the objective. Each ad line may have a different budget, and the budget will be based on how the campaign will best achieve its objective. The way that advertisers may do this is through optimization. Typically, in optimization, it starts with measurement. So measurement of things like clicks, sales, overall return against the objective. And then either a system will automatically update the budget for different ad lines, or users can manually update the budget in many systems, in many DSPs. And then it'll serve the ad and measure again. It's an iterative process typically. One of the things that we want to consider with campaigns is that many advertisers will have multiple campaigns. So consider an Amazon business like devices. For devices, we have Amazon Fire TV sticks, Echo Dots, Fire tablets. These are often run with different strategies that require different expertise and different marketing managers. Different marketing managers will therefore run campaigns separately to achieve those specific objectives. Now, when we talk about optimization, since each of these campaigns has its own objective, they'll also have their own ad lines. And when we talk about optimization for those ad lines, we're typically talk about optimization within the campaign. Many of the existing systems optimize campaigns in silos. In this case, this is a business that has multiple campaigns with multiple objectives, but still there's a unifying business. So one of the challenges that we want to consider with optimization is the learning time that it takes for the system to figure out the optimal mix, because it is an iterative process. It requires the campaign to deliver, measure, and then reallocate the budget and take a new measurement. Also, measurement is not always indicative of future performance. There's changes that will affect performance, such as seasonality, competitive bidding by other advertisers, privacy changes, and even changes within the DSP itself. So one of the ways that we think about addressing this is to share learnings across campaigns through these optimization approaches. Instead of looking at optimization within just one campaign, we want to look at ways to share learnings across campaigns. This would be applicable for businesses like Amazon that have many different campaigns running, and also for agencies that may have many objectives for different campaigns. We looked at the relationship between budget and clicks, and one of the things we observed is that it's heterogeneous. There are different, so each of these colors represents perhaps a different ad line, and each ad line will have different responses to clicks at different budget levels, which means that we need systems to continually learn, and it's not just always predictable.
Like others have done, we formulated this as a combinatorial multi-armed bandit problem. Campaign reward and overall return on investment across campaigns depends on outcomes associated with each marketing strategy, which is determined by the budget allocated to each ad line. In other words, this is an optimization problem where we choose a feasible allocation of budget across ad lines and campaigns to maximize the expected return. A notable feature of our algorithm is an embedded Bayesian hierarchical model. We've embedded a generalization layer into the standard combinatorial multi-armed budget setting that shares information across campaigns. There's also a random effect to capture the within ad-line heterogeneity that we observed in that scatter plot. Also, we have the flexibility to incorporate different types of models, including linear regressions, Gaussian processes, and neural networks. Here's our algorithm. Our learning strategy is to first update the posterior, and then second, using the derived posterior, use two-stage Thompson sampling algorithm to create feature-based expected return. Then finally, using dynamic programming to solve a multiple choice knapsack problem that determines the budget allocation. In simulations, we compare this approach with alternative algorithms that are less flexible or use less information. We also consider two practical advertising problems. First, budget allocation across multiple concurrent campaigns. And second, a scenario where campaigns are run sequentially and our algorithm is a principled approach to leverage historical data to inform current and future budget allocation decisions. You can see in these simulation results that information sharing and flexibility in our method pays off. Our algorithm generally outperforms the alternatives, and the more flexible the model, the closer we get to Oracle regret. Here you can see our algorithm is the purple and red lines. And as you might expect, we also see more clicks resulting from our algorithm, which here is the blue and the orange lines. We tested this online using an A/B test structure across 300 marketing strategies spread over 30 different campaigns. We saw a 13% increase in daily clicks after just 3 weeks. We're in the process of scaling this across Amazon's more diverse business lines, and we expect an even higher impact from that.